Yeah, now you have a big dump file and you transfer it somewhere, and it happens from time to time that this transfer goes wrong. There will be a corruption, or even worse, there's tampering happening. How can we protect ourselves here? How can we protect a dump file? And with 21C, we have a very good option to do that. First of all, you can, during export, generate a checksum. And the difference between generating the checksum by yourself instead of letting Datapump do it, when Datapump does it, first of all, you have a variety of choices for the algorithm, much, much better than the MD5. So as a SHA 384 is much, much better. But in addition, that checksum will be encrypted and stored in the dump file. So it's very hard to really go around that and tamper it. When you receive that file and you want to import it, the first check could be just a verify only, which now checks if the checksum is correct, still correct. And when you then do the final import, you may not want to have this checksum check running again, so you can skip it with verify checksum yes. Of course, this is just available from 21C on, so currently until 19C, you still have to deal with MD5 checksum, for instance. And for instance, when we upload something into the object storage there, we can verify this with DBMS Cloud and check whether the checksums are still correct. Finally, in the best practice section, most useful, especially in the cloud environments, to avoid any noisy neighbor disturbance, and especially also if resources are insufficient, restrict the number of Datapump jobs in a multi-tenant environment. I said cloud because we saw this coming up in cloud environments quite quickly with a lot of PDBs. And unfortunately, these max Datapump jobs per PDB and max Datapump parallel per job, those parameters are set so generously high that you easily can create a lot of noise. So it may be really useful to restrict both of them, especially in a multi-tenant environment, but really, really quite often in a shared cloud environment where we use multi-tenant. So keep that with you. If you search for the parameters, I think you may find also some useful MOS nodes. And with that information, we would like to conclude the best practices. And then Bill will take over and start with the second part of today's talk. Now we go more for the internals. Over to you, Bill.
Hey, thanks, Mike. Let's dive into the parallel feature of Datapump. Now, if you use the Datapump default for parallelism, parallel equals 1, a job starts with a minimum of 2 processes, a control process and 1 worker. The control process verifies the parameters in the job description. It controls and assigns work items to the worker. However, Datapump can export and import metadata and data in parallel. So you can optionally specify a degree of parallelism for the Datapump job. In the example here, we're using parallel equals 4. Now that degree of parallelism of 4 is the maximum number of active parallel processes, including active workers and parallel query processes that can be concurrently executing. It does not include the control process nor the shadow process. Any workers that are not engaged are sitting idle waiting for work, and Datapump will only start the number of processes that it really needs to complete the task. Now, if you're going to use parallelism, then you also need to specify multiple dump files for the parallel throughput. Now, the easiest way to do that, to specify a dump file set, is to use the %L wildcard character in the dump file name. Now, having multiple dump files avoids file locks, since a worker will lock the dump file exclusively when it writes to it. And using parallel or degree of parallelism along with the wildcard in dump file is necessary to have parallel throughput. You can also use parallelism on import. Locking isn't an issue here because the workers are only reading the dump files, and the degree of parallelism value for export and import are completely separate. For instance, if the target system has more resources available than the source, you can set a higher degree of parallelism for your import job than was actually used on the export job. By the way, you can even set or change the degree of parallelism after the job has started. Later in the webinar, we'll show you how to do that, how to change the parallelism for a running job using the interactive commands. Last topic I'd like to cover is introducing the data pump worker. What does it do and how is work assigned to it? So what does a worker process do during export? Well, the worker process may export metadata using the DBMS metadata API to collect object metadata for export. And on import, it would convert the metadata to DDL and PL/SQL for import. The worker writes the metadata it collects to a dump file, or in the case of network mode, it converts that metadata for execution. The worker process may also be processing data using the data layer to unload in the case of export, or load in the case of import, or move in the case of network mode import of the data from source to target. If you're doing a network mode import, it's going to use the DBMS_metadata API to convert the source database metadata for execution and move the data to the target. And finally, export and network mode import work in multiple phases. The export begins with one or more workers collecting metadata for export. The export can unload metadata in parallel with worker processes. For metadata export, each object path is a metadata work unit. Export collects the information as it progresses, and including finding table data items to export. It determines the number of workers for the metadata export, and it holds some of the workers in reserve if data is also being exported. Now, for data export, the table data metadata items include size estimates that drive the prioritization of the table data work item units. The table data item work units are scheduled as worker processes become available. Now, if the overall export time is dominated by data export, data pump's going to try to initiate that data export as early in the job as possible, and with as many workers as possible. However, it may not be possible to determine a true estimate of the data export time early in the job process if large table data items are not discovered early. Export can also be dominated by metadata export, for instance, in the case of a transportable table space export, in that case, it's only exporting metadata.
Thanks, Bill. Let me delve just a little deeper into what happens when you export metadata pre-12.2 or 12.2.01 and later, because that's the dividing line where we implemented parallel metadata export and import for data pump. What will happen is for your 12.2.01 and later databases, 18, 19, and so on, most metadata will be exported and imported in parallel. And I say most there because there are some types of metadata that have dependencies, such as types, where you might have a type hierarchy that needs to be exported or imported in a particular order due to type evolution. But for most metadata, we will export and import it in parallel now. So what did we do before 12.2? Well, before 12.2, when we were exporting, the very first phase that you're going to see in your log file is the estimate phase. And what we will do by default is we will look at where the data is laid out in your data files, and we'll count the blocks. So we'll go query the DBA segments, views, and so on to find out what are the biggest objects that we need to export. And that way we can get the right ordering to make the export as efficient as possible. But that estimate phase can be time consuming on a large database. You could speed it up by saying estimate equals statistics, but sometimes you don't have accurate statistics, and then that can throw off the export process itself. And only once we're done the estimate phase will we then start exporting the metadata with a single thread, and then we will also export the data using parallel processes. Well, we mix that up in 12.2 to make it more efficient. With parallel metadata export, we start exporting the metadata as soon as we know what it is that we need to export from the database. So we gather the set of objects we're going to work on, and while we are estimating the data sizes, we start exporting metadata in parallel. And again, it's most of the metadata will be exported in parallel. We're talking about things like users and table definitions and constraints and roles and so on. So if you look at your log file, you can actually see this difference in how we operate right there in your log file, especially if you use the metrics equals y parameter that I advised you to use earlier under best practice. Pre-12.2, what you can see is that we start with the estimate phase, and then only once that is completed do you see the startup of our other parallel worker processes. So that means we've only got one thing happening until the estimate is done, and then we start all those parallel processes to start actually doing the real work. Whereas in 12.2 and newer databases, what you'll see is we start up all those parallel processes right away, and then as soon as they can, they get going on exporting metadata, and eventually, after the estimate phase using statistics, we will start exporting data as well. So it makes the whole process much more efficient, especially for those metadata heavy databases like your SAP databases, your e-business suite databases, and other enterprise applications. So I mentioned this earlier in terms of best practice, but it's a really good idea to have up-to-date statistics on your sys and system schema, because both the estimate phase and all of this export of metadata is going to be a heavy user of dictionary tables and fixed objects. That will make your estimate phase and your metadata export go so much faster if you have good statistics there. So now let me just give you kind of a boxes and arrows type of example of how this really plays out in terms of processes. Let's say you've got 3 subpartitions that you're going to export here, and you specify parallel equals 6 for data pump. In this particular table, as I said, 3 subpartitions. And we're using a wildcard so that you get parallel dump files, which is the right thing to do. Now, how many processes would you expect to get out of this example when you said parallel 6? Answer might surprise you, because what you'll get, first of all, is the control process. So that's 1. And then you have 1 process that is unloading the metadata in this case. And then the next worker might look at a partition and say, that is above the threshold of size where we would use intra-partition parallelism of external tables. So instead of just unloading that data myself, I will call parallel query and invoke 2 PX processes to unload that partition in parallel. And then the next subpartition might be smaller. Maybe it's below that threshold. So we have maybe 1 direct path unload of that subpartition. And then the third subpartition, again, is larger and takes advantage of 2 parallel processes. So that gives you the 6 active processes that your parallel 6 that you specified for data pump asked for. You've got 4 PX processes and 2 worker processes, one on metadata and one doing direct path unload. The other workers are coordinating things. But what you also have are 2 currently idle processes, worker processes that aren't doing anything because you specified parallel 6, and we only want 6 processes unloading data at any given time. So even though you said parallel 6, we end up with a total of 11 processes here. We have the control process, we have 6 worker processes, and then we have the 4 parallel query processes running all at the same time. Now, some of those processes are idle, but it pays to remember that this can happen because the process count on your system may throttle the number of processes that you can spawn. So that's just a little bit of a look under the covers of how parallelism works for data pump.
Now, a worker process may use the dbms_metadata API to convert metadata to DDL and to PL/SQL for import. A worker process may also use the data layer to load or import the data. A network mode import uses the dbms_metadata API to convert the source database metadata for execution and move the data to the target database. Now, import assesses all import tasks by reading the control table from the dump file. It determines ordering requirements, mostly ordering the import by object path. In general, the object path is strictly followed for import. Table data cannot be imported before the table, but individual table data items can begin as individual tables are created. And parallel metadata import even works when the export wasn't done in parallel, such as if the export was done in a release before 12.2. Furthermore, the parallelism on the export and the parallelism on the import are completely disconnected, so you can have much more parallelism on the import than you could or might have had on your export. 12.2 has much more parallelism for metadata import. Everything is imported in parallel except the items with dependencies, type hierarchies, schemas, and procedural actions. There are 2 types of data pump parallelism here at work. One type is applying or allocating a worker per petition or sub-petition or per small table. Over a certain threshold, for a large petition or a large unpetitioned table, a worker can be a coordinator for multiple parallel query processes. Now, a bit about the internals. Metadata is exported in XML documents from the dump files. Each XML document contains a certain number of objects of a given type. One XML document is allocated to a worker at a time. So for example, if there are 162 user objects to import, there are going to be 2 workers that each get to import 80 users per XML document. And then one worker is going to import the last 2 users, while other workers may actually remain idle. Now, this works for conventional dump file imports as well as transportable tablespace imports since release 21C. The restart works the same as always, and the status command will show multiple workers on the metadata. Now, here's an example of log files, snippets from log files, where we can see the difference using parallel equals 8 versus a pre-12.2 import that was not using as much metadata parallelism. So here you see that there's one worker performing all the work, taking about 50 seconds, versus with parallel equals 8 on the metadata, you get 8 parallel workers completing the task versus the single worker for pre-12.2. And notice the difference in the completion time. It's down from 50 seconds to about 14 seconds, about 5 times faster. And finally, looking at a performance comparison. Now this is a performance comparison for an EBS test database. The numbers are in seconds, and it shows that the 12.2 import with parallelism is considerably faster than the 11.204 import, notably for tables, for grants, for packages and views, and especially for indexes.
Thanks, Bill. So is there everything parallel? Yeah, not always. There are a few things which, unfortunately, in 19C don't get progressed parallel. So first of all, the network import does not support loading metadata in parallel. Now you may ask yourself, is that an issue? Well, if you have like 500,000 partitions and subpartitions, that may be an issue at some points. Second thing is, there's no parallelism for basic lob files. You may know that from some experiences when you exported a database with data pump and you had basic lobs, the old lobs since 8i there, and it went really, really slow. But we told you before, the relief is very simple. Convert them to secure file lobs. Use dbms redefinition or a 19C online table move that allows you to move from old basic file lobs to secure file lobs. And another thing to mention, there's no parallelism for metadata export and import with transportable table spaces. And we face the same problem, like you have database with 500,000 partitions and subpartitions, and then things can become really, really slow in the metadata phase. So when you export what is in your table spaces and when you import it again. Good thing is, this is there since 21C. Now, for most of you, that will mean with the next long-term support release 23C, but at least it's coming, it's there, and we heard you. And with that information, I hand over now to Venkatesh for faster patching.
Hello, my name is Venkatesh Sangam. I'm the Software Development Senior Director for the Database Utilities team. In this session, we're going to cover faster data pump patching using dpload, as well as data pump bundle patch. dpload is what gets used to patch data pump. Traditionally, this has been slower because it's rebuilding all of data pump as well as metadata API changes, along with ensuring that all the dependencies are handled correctly. As you can imagine, this is not the most optimal approach to rebuild everything, irrespective of whether the objects have changed or not, and dropping and recreating them. So that is why we had to invest in a new and improved dpload so that we can get faster, reliable, and cleaner approach to patching data pump. So what does this new and improved dpload do? This basically ensures that patching performance is improved by up to 90%, as well as it reduces the number of invalid objects by up to 90%, and also up to 0 in a subsequent patch. So which means that as and how you continue to use dpload, you will actually eliminate all the invalid objects in the system. This also reduces contention because the scripts that the dpload calls have been refactored and split into a much more granular set of things so that we can actually have better control on contention as well. So in effect, basically it reduces the patching time, it reduces contention, and it eliminates invalid objects up to 0 in subsequent patching, as well as in some cases when the initial patching may take up to a few minutes, whereas the subsequent patching will be close to a minute. And again, it depends on the number of objects that have changed. This slide shows the distinction between what we call as a dpload patch, as well as what a data pump bundle patch is. The dpload patch is basically the patching infrastructure change that we have done to improve the patching performance and make it more reliable. It does not require any downtime to install, and it can be installed into an Oracle home, into a running system without needing any downtime. This also is rack rolling, meaning on a rack-enabled environment, we can apply this without needing any additional downtime. On the other hand, data pump bundle patch is a set of functional fixes, and which basically improves the running of the data pump job itself. Now, it does have a lot of important fixes, and it does mean that this is not rack rolling because it has functional fixes. In some cases, it may need downtime, which means that you cannot apply while the data pump job itself is running. So as long as the data pump job is not running and it's not in use, this is non-binary online patchable. This slide shows that the data pump patch as well as the data pump bundle patch can be installed independently. The data pump bundle patch, the data pump patch itself can be installed on its own without requiring a downtime, and any subsequent data pump patch apply will make use of this new infrastructure to make it more faster and performant patching. The data pump bundle patch is tested with every RU starting 1910, and the patch numbers are listed here.
Okay, it's time for the final section of today, Data Pump Extreme. The first thing that we will cover is SQL file. You can extract metadata from a dump file using the parameter SQL file. What does it mean? Well, if you have already exported your data, your schema into a dump file, you can use data pump import to investigate that dump file and extract the definition of the metadata and put it into a file. You don't have to actually import the entire dump file in order to investigate the definition of the metadata. No, you can simply just extract the definition and put it into a SQL file. When you start data pump import and you've specified the SQL file option, data pump will not do an actual import of the data. It will just extract the metadata and put it into a file. If you have a dump file that contains a schema-based export and you extract the metadata, it'll look something similar to that. First, data pump needs to create the user, in this case, TPCC. Then apply grants, and then start to process the metadata, tables, indexes, and so forth. All that will be put into a file that contains all the statements that data pump would eventually execute. How can you use the SQL file? What is the use case? Well, one of the use cases is when you need to create really big indexes. So imagine a schema that looks something similar to that. We have 10,000 small tables and one really big table. We also have 10,000 small indexes and we have one really big index. We learned previously today that when data pump creates indexes, it'll create many indexes at a time, and each index will be created with a parallel degree set to 1. That is very efficient if you have many small indexes, but it is also very inefficient if you have some very large indexes. So let's get the best of both worlds. We will let data pump create the small indexes, and we ourselves can create the big indexes with a parallel degree that we find is suitable in this situation. So if you head into the source database, you could query user segments to find the indexes of interest, the big indexes. How big should they be? It depends. In this case, I found 3 indexes, big 1, big 2, and big 3. So when I import this data, I will exclude those indexes from my import. The tables that the indexes belong to will still be imported, but not the indexes. Then I can combine the include clause with the SQL file clause to extract just the metadata information of the 3 indexes, big 1, big 2, and big 3, and put that into a file. I can then investigate the file, extract the DDL statements that I need to create the indexes, and then create the indexes in the database with a parallel degree that I find suitable for this specific case. I've prepared a small demo where we can see this use case work. First, let's investigate the schema and perform an export. So we connect to the database as the schema app, which is the schema that contains the tables and indexes. By querying user tables and user indexes, we can see that there are 10,001 tables and the same amount of indexes. Also, by investigating user segments, we can see that there is one big table and one big index. All other objects are really small. So let's go ahead and export the schema app. I've set parallel degree set to 8, multiple dump files, and no statistics. I'm connecting to the database as DP user. That's the user that will be doing the export, and I refer to the parameter file. Now the schema app is being exported into my dump files. There we have it. So now let's try to import everything. Allow Datapump to create everything, including the big index. So I have a parameter file. It's very simple. I import everything using a parallel degree set to 8. Again, I start Datapump import impdp and refer to the parameter file. Now Datapump will start to create everything, including all the 10,001 tables, including the big one, all the indexes, including the big index. So we'll be creating the big index with parallel degree set to 1. Okay, it completed in almost 27 minutes. Now let's try to redo it, but we will exclude the big index from the Datapump import, and we can do that in our parameter file by setting exclude parameter to index and then specify the name of the big index, in this case, big 1. So we will leave out the big index, but import everything else. All the metadata, all the tables, all the indexes, and this time a little over 21 minutes, but we are still missing the big index. So we have a new parameter file where we are combining include and SQL file to just generate the DDL for the missing index. Let's start Datapump import to generate the SQL file. That's fairly quick, and let's have a look. Here we can find the DDL, the create index statement for the missing index. So let's grab that. Oh, you can see here parallel degree 1. That's not very good for a very big index. Grab the create index statement, connect to the database as the app user. And now let's create that big index. But notice that I've changed the parallel degree to 8. So now we can create the index much faster than Datapump would have. In this case, it takes almost 3 minutes to create that big index. So now we can reset the parallel degree on the index. And now let's do a comparison and compare the numbers. In this case, we could save almost 3 minutes by creating the big index ourselves instead of letting Datapump do it. So is it really worth the effort? We saved 10-15%, almost 3 minutes in this case, but I also had to do some manual work. So is it really worth the effort? And as always in IT, the answer is it depends. This was a fairly small example. The index was only 5 GB in size, but imagine you have a very large database with some indexes that are 10, 50, 100 terabyte in size. There, it really makes a crucial difference if you can put a proper parallel degree on the index creation. So this could be a really good use case for using the SQL file option that you can find in Datapump. If you need to extract the definition of an index or any other object, instead of using the SQL file option in Datapump, you can also use DBMS metadata directly. That's one of the APIs that you can use as well. DBMS metadata has a function called getDDL that you can use to create the DDL statements for any object in the database. And Datapump, in fact, uses the DBMS metadata API as well, but it's free for you to use it as well. Now over to Rodrigo for some more extreme features.
Thank you, Daniel. This is water, by the way, at least this time. So now let's talk about DBMS Datapump usage. So we know very well ImpDP and XPDP, which are the binaries we use to run the export and import with Datapump. However, those binaries, they translate the parameters that you provide into DBMS Datapump API calls. So what really executes in the backend is the DBMS Datapump package in the database. This package, by the way, do further calls in another APIs, like the external table API, if you're using external table access method, DBMS metadata to get the metadata of the objects, and also direct path APIs. Those are just examples of some APIs that are used by the DBMS Datapump API. So we all use, again, DBMS Datapump through the XPDP and ImpDP. Okay, but you can do it straight away. You don't need to go through these binaries. And this is very recommended. So we have some tools that do that, like zero downtime migration, Enterprise Manager, SQL Developer, SQL CL, also ORDS, which is the Oracle REST Data Services. And you can also write your own tool, or you can write your own PL SQL block to do it. It's documented and supported, and we have it in Oracle official documentation. So here are just some ideas of things you could do with DBMS Datapump API. You could, for example, I see a lot of customers creating the export script in the OS layer with cron tab. So we have a cron tab job that we'll call XPDP. However, you don't need to put it in OS layer. You can put it straight on the database. You can write, instead of a shell script, you can write a PL SQL block and call it, instead of using cron tab, using the DBMS scheduler. It's much more simple. You don't need to store your password in text files or call Oracle Wallet. It's already inside the database, so it's much more simple in that sense. Also, you can put dynamically things on that, maybe based on the number of schemas, you maybe increase the number of parallels, for example, or get the schema names from a certain table inside your database. So there is a lot of logic you can put there. Also, for example, there is an article I wrote about 7 years ago about how to rename a schema using a loopback database link. This article, it's based on DBMS Datapump API. So what I do simply is put a database link, point to the database itself, and then I call the DBMS Datapump API to run an ImpDP using this database link, but I use the remap schema. So I change the name of the schema, meaning that I clone the schema. So that's a way for renaming the schema. Also, you could possibly take a snapshot of a given schema during application development, for example. So those are just some ideas. Now let's see how client calls are translated into DBMS Datapump calls. So imagine here you have an XPDP. Here is schemas equal to app. The first thing you would do if you are using DBMS Datapump API is start with this open procedure. So the open procedure will instantiate a new job. And here H1 is a variable that will have the ID for this execution. It's a handler that will store a unique ID for this call. Now from this point, everything that we want to change in this export job, we are going to use this H1 variable. So for example, again, the schema is equal to app. So we need to add a filter here. So we use the metadata filter procedure, and we specify that the schema that we are using is just the app schema. Also, we have a dump file. So you use the add file procedure. And here in file type, you see that we are adding a file type dump file, meaning we are adding a new dump file to this process. The same applies for the log file, but the file type here for the log file is file type log file. What about parallelism? you can use the set parallel procedure from the DBMS data pump API. So the set parallel here, we put degree equal to 4, the same value we put on the command line. But this is one of the advantages we have when we run this from inside the database. So here in this example, as you can see below, I'm getting the CPU count we have in the server and put in this variable. If you want to do this in the shell script, you would need to connect first on the database, get this variable, and put this in an OS variable, and put this OS variable in the parallel call of your XPDP binary call. So it's much more complex. Here I'm getting straight from the database that I'm already inside. And matrix equal to yes and log file equal to all, we can use the set parameter to define those variables as well. And finally, we start the job. So start job here, I'm passing the handler, and then this will put the job in background. I can officially call this wait for job that's gonna wait for this job until it finishes and store in this job state variable if it was successful or if it failed. So now I can see what is the status of my job. Imagine now that you already have your script developed using the XPDP command or the NPDP command, and you want to convert it to a DBMS data pump call. You can rewrite it from scratch based on the slides that I just showed you, or you can use this event 146 to get what are the actual calls in DBMS data pump API when you run the command on the binary level. Remember that this system event is a bit resource consuming, so only try it on lab or test environments. So here first, what we do is we enable the SQL trace on this database. Then we finally call the XPDP or NPDP. After we run XPDP or NPDP, we will have in the trace file all the DBMS data pump commands that were called by the binary NPDP in this example. So again, use DBMS data pump. It's a very good API. It's very well documented, and everything is in the Oracle docs. We have very good examples there. Now it's with you, Bill.
Thanks, Rodrigo. Let's talk about restarting export and import jobs. Later in the webinar, we will show you how to stop and start a running job. Export can be restarted after the estimate phase of a job is completed. This is because the worker processes report job status by entering rows in the control table. The control table contains different types of rows, one of which is called the type completion row, as we see in this example. There is one completion row for each type of object that is exported. In this simplified example, we're showing table spaces and users. In this example, the export of the table space object type is complete, and the user type has started. The first user object that was exported set that time. Then, as we'll see in the next slide about restarting of an import, workers create object rows in the control table for each object of the user type. If all of the users were exported, the worker process would have updated the user completion row with a completion time. In this case, upon restart, a worker process detects that the users were in the process of being exported but didn't finish because there is no completion time. Data pump drops all of the rows that describe the users, drops the completion row, removes the XML stored in the dump files that describes the users, and then it configures the metadata API to start after table space, since table space is the last complete object type. It's worth noting that if a job is stopped intentionally using the command line interface, the stop command stops the job and allows it to be restarted. However, the kill command stops the job and removes the control table. Once the control table is removed, the job cannot be restarted. Imports can also be restarted using the control table. The tables scott.emp and scott.department were exported along with their indexes. After successful export, the processing_state column for each object row in the control table has the value R. designating retrieved or exported. And the value C in the processing underscore status column indicates that the objects are current or successfully exported. This is the starting point for an import. If an import job is started and then stopped, for instance, after the table scott.emp is imported and before the table scott.department is imported, the rows look like this in the control table on the slide. The value W is the state field, indicates that the table scott.emp is written and imported, and the value C in the status field indicates that the objects are current or successfully imported. The value U, or unknown, in the status field for the table scott.department indicates that the import started but did not finish. When data pump import restarts, it looks for a row with the value U in the status field and continues with that object. In this case, the table scott.department will be imported again. After that table is created, the import job will continue with the remaining objects. In this case, it will be the two indexes that have an R for retrieved or exported in the state column. Now back to Roy for more on the interactive commands.
One of the little known features of Oracle Data Pump is the interactive command mode, which can give you a lot of control over a running data pump job. So let's take a look at it. The purpose of the interactive command mode is to be able to modify and query the status of a job so that you know exactly what's going on and can maybe change it in ways that would help performance or maybe compensate for other workloads on the system and do other things to the job that you might have forgotten to do in advance. So I'll give you an example of some of the commands that you can use. Now, it's important to recognize that some of these commands apply to both export and import, such as getting the status of a job, for example, or modifying the parallelism of the job while it's running. You can even change the tracing on a job and implement tracing if you decide that you need to diagnose some issues with it. But others may only be export or only on import. For example, the file size, the ability to change the dump file size that you are producing is, of course, only available on export because on import, the dump file size is already set. There are a wealth of commands that you can issue from the interactive command prompt to affect a running job, and you'll find those in the documentation. So now the next question is, how do you issue those commands? How do you access this interactive command mode? And there are two ways to do it. One is to simply hit Control-C during a running job. That will bring you to the interactive command prompt. You can issue commands and then tell the client to continue by issuing the continue client command. Another way to do it is to use the attach parameter on the data pump command line. You could have a data pump command running in one window and then in another window attached to that job and be able to monitor and affect that job using interactive commands. So I'll give you some examples of this in a very brief demo here. So let's just say that you start off and you've got a very simple export here. As you can see, it's a schema export, and we're just creating multiple dump files. But oops, we forgot to specify parallelism here. So this could impede our performance because we know we've got a lot of objects that we want to export here. So it started, and now we realize, oh, we forgot to specify parallelism. So we can break into the job with Control-C, and we can get the status of it. What that will show us is that there will be one and only one worker because our current parallelism for the job is just one. We didn't specify anything greater than that. We can then increase the parallelism for the job, and that will take effect immediately. When we continue the client, we will see the job progress, and then when we get to tables, we will be exporting multiple tables at a time. Now, another way to get to this would be to use the attach parameter using the job name. That is one of the very first lines in your data pump output is the name of the job. We can look at the status of it. And now we see that we have our current parallelism of the job is 4, and we have multiple workers spawned. Now, it's interesting that a couple of these workers seem to be idle at this point. And why is that? Well, look at the worker parallelism for worker 3. That's set to 3 right now. Worker 4 has a parallelism of 1. So what's going on here is that worker 3 has spawned 3 parallel query processes to do its work. Worker 4 is doing more work on its own. So you get now those 4 parallel processes, very similar to what I described earlier when I talked about export parallelism. So these interactive commands can really give you a look under the hood to see what's going on in the data pump engine, as it were, and allow you to control it, to manipulate it as a job is running. So I hope you find that useful. Now I'll hand you off to Mike for some troubleshooting tips.
Thanks, Roy. And this brings us right away to the last topic for today, troubleshooting. Of course, we don't want to talk about that, but sometimes it's really helpful and it's actually key to help you progressing on your work. So in case of any issues, data pump not doing what you expect data pump to do, you open a service request. Now we would like to guide you which information you could check by yourself and which information is really helpful in case you open an SR. What should you upload? Let us start here with the first thing, the log files. And we talked about that before because it's really key if you open an SR that your data pump log files have been created with matrix yes and log time all. So you see here on the slide that the information is very different, and without the worker information and the exact timings, it's really, really hard to tell anybody and anywhere what has gone wrong or what has taken too long. So we need that, and you need that basically. But we told you before, that is really important. In addition, and I see often SRs where this has been simply forgotten, check by yourself your alert log and upload it with the SR. So here you see that the control process has written a message in the alert log. How do I see this is the control process? Because the DM00, D is for data pump and M is for the master. So this is the control process kicking in and starting with the job. I will repeat that later on. Here you see a standard generated job name. I highly recommend you that you define a job name by yourself, because when you troubleshoot, it makes your life really much, much easier when you have an individual job name for your data pump job to identify it in the queries, in the tracing, everywhere. Then, in addition, data pump workers and also the control process, they write trace files occasionally. So in the same directory where your alert log is, in the trace subdirectory under the diag tree, you find the trace files. Here again, in the top line, the brownish box, you see it has DM. This is the control processes trace file. And with that information, we find a lot of things already, what the job has been done, especially if something was slow, hanging, or taking too long, or doing strange things. Next thing is database views. Inside the database, we can see a lot about data pump already because it's using the API. And first of all, the most important view is DBA or CDB data pump jobs. There we can monitor the progress of a data pump job. And in this case, we have some really, really useful MOS nodes, very detailed with all the queries. So the output here from my job, I show you what it's doing, in which state it is right now, and how many sessions it created. That is just by using a query from that MOS node. And again, second time, the recommendation. If you want to troubleshoot data pump, if you want to dig deeper, it's almost key that you define a job name by yourself. So here my job name is my EXPDP1, and this makes it much easier to identify the data pump's job later on. DBA data pump sessions tells you then about the SQL statements a data pump session is executing right now. And this is extremely useful in case of a hang or a very slow operation. So when you have the feeling that data pump is not really progressing, what is it doing? Then this can help you. And again, the MOS node is extremely helpful, giving you detailed queries to figure that out. And this brings me finally to $session long ops. Most of you may know this view in the database already. Here we find out quickly how far data pump has been progressed. Because in the so far column, it tells us how many megabytes it has progressed. And this in relation to total work, the projected maximum megabytes data pump will work on. This gives you a very good information where data pump is right now and how far it will go at this point. This brings us then, if that hasn't helped and figured it out, to the final point, the tracing. Again, we have a very, very detailed MOS node here showing you all the trace options for data pump. And if you want to trace, your user needs to be a privileged data pump user, meaning it needs the exp full database or the imp full database role. And make also sure that your max dump file size is big enough, because when you start tracing, you get a lot of trace information, and these trace files tend to become very quickly very big. We have three options to trace. We can trace, first of all, with the trace parameter. So this would be in your par file, or if you're brave enough typing everything on a command line, then put it on the command line. Then the interactive mode, and as third option, put it into the SB file. And let me start here with the trace parameter. So we put it usually in our par file, and this allows tracing even of individual data pump components. So if you want to trace only the workers or only the control process or only the metadata API or whatever, it gives you full control. Still, normally you won't need that. You use that trace option 1FF0B00, and this gives usually enough information even for us in development. So normally we just go with this trace option. You can do full tracing with 3 Fs there, as you see in the slide. But in most cases, that is really not necessary to find out what has gone wrong. When you need more trace information, please revisit that MOS node. It gives you a lot more control and is very well documented there. It generates at minimum 2 trace files. One trace file is for the control process, having the M for master in it, and then at least 1 trace file for a worker. But for each of the workers, there will be 1 trace file. So at least 2 trace files will be generated in the trace directory. And these are the ones you need to upload then with your service request. Then you can trace also in interactive mode. If data pump is running now and you hit a slow situation, no worries, or maybe it's hanging at some point. Then you type Control-C, as we showed you before, in the interactive mode. You are in interactive mode now. Now you attach to your process, to your job. And again, it's very helpful if you have defined a job name in this case. And then you use a trace option. Here we use a different option. But as I said before, the 1FF is the most liked one by us because it has the most important information in it. If it's really hanging right now and not progressing, you can start your job and use the skip current equals yes option, because that will skip the current action and then go on to the next one. That could be useful in such situations as well. And then you can put it also in your SP file or in Aura. So here the event for data pump triggering the trace is 39089. So you would put the event equals 39089 trace name context forever, colon, level, and then the bit mask for the trace event. Not used so often, but you could. Generally, when you deal with such problems, and I think we showed you that before, event 10,046 is really helpful. It's the first event when you start in Oracle support. I think this is the first thing you learn on day 3, how to use 10,046 SQL trace event, because it traces everything happening in a database. And you have certain levels, so you can go to level like 8 or 12 to have the binds and the waits. The waits will be really important here. Binds may not be so important. I use usually level 12, to be frank with you. And this gives me a lot of information. When you have that information, run it through tkprof, and then you get a readable output from that. That is really quickly done. And I think all that is described in this very useful MOS node about 10,046.